So, dear students, we are continuing with the discussion which we started in the previous video and looking at what makes whole numbers whole. Whole numbers basically means that we are adding a new number to the natural numbers or counting numbers, and the meaning of whole basically indicates something which is complete or something which can stand on its own. That's the meaning of it. So looking at that aspect, let's have a deeper understanding of why whole numbers are called whole. So, and that would be better done by continuing the discussion which we had in the first and a video, that was the previous video where we discussed about natural numbers, and that deals with counting the number of boxes. So suppose we have a box and we are denoting that box by drawing a line, and naturally that means two boxes. We'll be denoting that two boxes by two lines, or two. And here, what if we take one of those boxes out, in the sense that there are two boxes, we are denoting it by two lines, or two, the number two, and we are taking one box out. And how will we symbolically represent it? That will be basically 2 minus 1, that is 1. Of course, it's 1. Now, let's interestingly continue the process and remove that box also. Now, the thing is that how will we represent the fact that now there's no box left to represent, or how will we represent the fact that there's nothing to count? So there's no box, or basically 1 minus 1 is 0. So you can see that as far as numbers are concerned, the first key problem when we first begin with natural numbers or counting numbers is to represent, or is to cook up a symbol which represents there's nothing left. So it obviously means that 0 is the next natural idea or concept to come after the natural numbers or counting numbers, which start with 1 and goes all the way up to infinity. Basically because 0 indicates that there's nothing to represent. 0 indicates that the counting numbers which were denoting distinct objects now is looking at no presence of any distinct object. So it obviously means that 0 is a fantastic discovery. The symbol 0 represents an emptiness or nothing to count, something like that. So that naturally leads to the a very obvious development, very important development, that when we add 0 to the natural numbers, that when we add a concept which denotes emptiness to the set of natural numbers, the natural numbers becomes complete. So it means that when we add 0 to the set of natural numbers, that is 0, 1, 2, 3, all the way up to infinity, the set becomes complete, and it is getting a new name, that is the set of whole numbers denoted by capital W. A very interesting point is that suppose we are looking at an operation like the Euler's number E times iota raised to pi. Pi, of course, is a radian measure. That's tough to calculate, but what about EI raised to pi minus EI raised to pi? Of course, we can see that the answer is 0. This example has been put here to indicate that emptiness, the concept basically means that you are removing everything from a particular object or a particular application, and 0 denotes that emptiness. 0 denotes that application isn't existing. Now, looking at the properties of whole numbers, first is the property of closure, the closure property, which works for addition and multiplication. Important point which I'd like to state here is that students are requested to view the first video to see a detailed description of the properties because the same idea, the same concept, the same theoretical principle is being continued here also. So please don't forget to watch the first video dealing with natural or counting numbers. So closure property for addition, multiplication. Commutative property works for multiplication and addition. Quite the same thing for associative property, which also works for multiplication and addition. And a new property is that of distributive, which is a distributive property of multiplication over addition, and identity property for multiplication and addition. So those two new characters which are coming up, that is the distributive and identity property, that's what we'll be looking at in this video, because the other theoretical principles were discussed in the first video. So what is the distributive property of multiplication over addition? For example, 90 times 12 can be rewritten as 10 plus 2. So that is something like 8 times b plus c, that is ab plus ac. So that is 90 times 10 plus 90 times 2. Of course, that is 900 plus 180, and that would be 1080, that is 1080. So we can see that it's multiplication over addition. Now let's look at a very interesting property, that is the additive identity. It basically means that any number plus 0, any number when added on to 0 retains the number. You get the same number. Why? Because 0 denotes emptiness, so nothing happens. No property changes with relation to that number which we are adding on to 0. That simply means 9 plus 0, you get 9. 9.99 plus 0, you'll be getting 9.99. Root of 9.99 plus 0, also you'll be getting root of 9.99. Now the point that 9.99 and root of 9.99 doesn't represent the numbers you get as results doesn't represent numbers which belongs to a set of whole numbers. So the next one is multiplicative identity. This is another very interesting property where any number times 0 will be getting 0, which basically means that 9 times 0 is of course 0. 9.99 times 0, which of course is a decimal number, you will be getting 0. Root of 9.99 also you will be you'll be getting 0. So that's a very interesting development. Now as far as the properties of whole numbers are considered, the same identity property doesn't work for as far as as far as division and subtraction is concerned. So not that point. So that's about why whole numbers are denoted so, and the properties of whole numbers. And in the next video we'll be looking at the next set of numbers, that is integers.